the mean value theorem. It is one of the most important themes in calculus. So today, let's discover this together. To arrive at the mean value theorem, we first need this Rolle's theorem. So first, let's take a look at this graph of some typical function that had this three conditions. Continues on the closed interval a to b. So see this function from a to b on this closed interval has no break. So it's continuous on a to b. And differentiable on the open interval a to b. Differentiable means the duality exists. So on this open interval a to b, at any point you can draw the tangent line. The slope will be a real number. The slope exists as a real number. So then the function is differentiable on this open interval a to b. So it's a nice smooth curve. And the slope is never going to be undefined. So it's going to be real number. And number three, fa equal fb. So fa, that's the function value at this endpoint. fb is the function value at this endpoint. fb equal fa here means these two endpoints are at the same level. So this four over here satisfy this three conditions, three hypotheses. Number one, continues on the closed interval a to b. Differentiable on the open interval a to b. The duality always exists on this open interval. And at the two ends, fa will be equal to fb. So they're at the same level, the two endpoints. Now take a look at this function over here. What do you observe? I'm trying to discover some theme over here. So what do you observe?
There's only one maximum for B.
Yeah. Oh, you talk about the extreme value theme. Yes. Continuous function on closed interval has absolute max and absolute mean. That was the extreme value theme. Yeah, I'm glad that you remember that. But today, we are going to talk about another theme, which is, so let's discover that together. So you observe that there is at least a point, see a point right here on the graph. The tangent line, what happened to the tangent line? The tangent line is horizontal. Yeah, horizontal. Therefore, the duality at this C here is equal to 0. So over here, you see this is a point. Over here, you see 2 points. 1 point here and this another point over here. The duality will be equal to 0 at this 2 points, right? And then over here, you have this 1 point here, the duality equal to 0. Over here, actually, for all the points between A and B, pick just any C here between A and B, then the slope for the tangent is always equal to 0. So you can have 1 point, 2 points, you can have infinite many points. Then at that point, the duality will be equal to 0. So we observe that. Let me write down the observation. So it appears that there is at least 1 point, at least 1 point on the graph where the tangent is horizontal, and therefore the duality is equal to 0 at that point. So that's our observation. So it is if the function satisfies these three conditions over here. Actually, it is proven. It's called the Rolle theorem. So Rolle theorem says that if the function satisfies these three hypotheses, if it's continuous on this closed interval, differentiable on this open interval, and fa equal fb, the two ends are at the same level, then what happens here is guarantee that there is at least a number c such that f prime of c equal to 0. So slope of the tangent at c will be equal to 0. Yeah, so that is the Rolle theorem. The proof of this, I make a video for that. So you can watch that later. So let's apply Rolle theorem to this position function of a moving object. So let's go for this. So over here, when you have this ball going up, and later on fall down. At these two different moments, they have the same position. They're at the same level. So f of a equal fb. At time a and time b, they have the same position. Position function, it is continuous on a to b on this closed interval. Okay. So, and also the velocity exists at any moment. So velocity exists means the first derivative of the function exists. So that implies that the function is differentiable on this a to b. So it satisfies the three hypotheses of Rolle's theorem. So Rolle's theorem says that there is at least a moment, there is at least some instant of time, the derivative of the position function will equal 0, which means the velocity equals 0. Let me write it down for you. So Rolle's theorem says that there is some instant of time t equal to c, c in this open interval AB, such that the derivative of the function f, which means is velocity, will be equal to 0. So guarantee that, right? Okay. But when is that moment? The velocity equal to 0. We learned that from physics. When you shoot this ball up, and then later on it fall down, right? At this highest point, the velocity of the ball is equal to 0. At that instant, at this moment, C between A and B, the velocity of the ball will be equal to 0. Okay, so you can try to understand that by this example in physics. Now here's another example. So we are given this polynomial function. This is a cubic function, okay, on this closed interval 0 to 3. Let's verify that this function satisfies the three hypotheses of Rolle's theorem. So what are the three hypotheses? Right? It is the function has to be continuous on this closed interval. Number 2, the function has to be differentiable on that open interval. Number 3, at the two ends, they are at the same level. F of 0 equal to f of 3. Okay, so let's check these three hypotheses, see if this function here satisfies. Number 1, we say the function here satisfies the first hypothesis. The function is continuous on 0 to 3 because why? Why this function is continuous on this? What kind of function is this?
Polynomial.
Yes, yeah. Polynomial function. Yes, you guys got it. So because the function f is a polynomial function, polynomial function is continuous on all real number, so certainly it's continuous on that closed interval. You got it, okay? The second one, the function is differentiable on this open interval 0 to 3. Why? Differentiable means the derivative exists. So you take the derivative, so f prime. So take the derivative of this polynomial function, we get 3x squared minus 2x minus 6, which again, it is a polynomial function. So it certainly exists. Okay, it's never going to be undefined. Okay, so this derivative exists. That's what it means to be differentiable. So that exists for all x in 0 to 3. Actually exists for all real numbers. So certainly exists in this open interval. Okay, so satisfy the two hypotheses. Okay, the last one. F0 equal to f of 3 because f of 0 here is equal to 2, substitute 0 in x. Substitute 3 in x, you get 3q minus 2 squared minus 6 times 2 plus 2. Do the calculation. Tell me what you get.
2.
You get 2, right? So you see that they are equal, right? This is 2, and then this is also 2, right? So they are equal, the same. So the function satisfies the three hypotheses of Rolle's theorem. Therefore, we can use Rolle's theorem to conclude that there is a number c in 0 to 3 such that the first derivative will be equal to 0, right? So, but how do we find that? Okay. How do we find those c? To find those C that satisfy this conclusion of Rolle theme, now we already differentiate the function, right? So differentiate the function, we got this 3x squared minus 2x minus 6. And f prime of C equals 0. So you solve for, you set that equals 0 and solve for C. Okay, so we solve 3c squared minus 2 times c minus 6 equals 0. So f prime of c is equal to this. So substitute c into x. So this is f prime of c. And we set that equal to 0, and then we can solve for c. To solve for c here, I already tried that. I couldn't use try and error to solve this. So I had to use the quadratic formula to solve for c. Okay. So remember what's the quadratic formula? Do you guys remember? You guys got it. Quadratic formula. Let me refresh your memory. For any quadratic function, ax squared plus bx plus c equals 0, where a, b, c are real number, and a not equal to 0, then x is equal to, so x equal to this. So there's a way that to remember this quadratic formula. You can actually sing it. It's almost Christmas. So there's a jingle bell version of this quadratic formula. So it goes like this, okay? So today I'm going to sing for you guys. X is equal to negative b plus or minus radical b squared minus 4ac all over to a 8.
Wow.
So yeah, so that was the quadratic formula, jingle bell song. Now we can use the quadratic formula to solve for c here. So c is equal to, now do the calculation, simplify it. Okay, later on you have to divide up and down by 2. Okay, then you got this part right here. So c equal to this. However, we're looking at inside this open interval 0 to 3. Okay, so one of them doesn't work. Which one doesn't work? Which one is not inside here? The one with the minus. The one with the minus is not in it, right? The one with the plus is in it. The one with the minus is actually negative, so it's not inside this open interval. So in this open interval, only the one with the plus here is going to be inside that. Okay, so in this interval, c is 1 plus square root of 19 and then over 3. We found that number c. So we found all those c inside this such that the derivative t will be equal to 0. You have a horizontal tangent when c equals this. Okay, do you guys get it?
Yeah.
Okay, that's good. Okay, thank you. Thank you for feedback. Okay, now move on. So example 2. Oh, it's going to prove this. We're going to prove that this has exactly one real root. I'll actually make a video of this. I post. Okay, I can. You can watch it later. Okay, the proof. Now the mean value theorem. That's the important thing. Let's abbreviate this as MVT. MVT. Now the mean value theorem is kind of similar to the theme that we went over, Rolle theme, except you take away the last hypothesis. We take away FA equal FB. So in this mean value theorem, you only have these two hypotheses. The function f is continuous on this closed interval AB, and it's differentiable on this open interval AB, but it's not required FA equal to FB. When you have this, then what happened over here it is, then we have this conclusion. There is a number C in AB such that this is going to happen. Now you might wonder, what is that? What does it mean? Okay, so I'm trying to help. I will try to help you understand this. Okay, so basically it means that f prime of C. So when the function is continuous on this closed interval AB and differentiable on this open interval AB, then what happened here is there is at least a number C between A and B such that the tangent line over here is going to parallel to this second line of this endpoint, this two endpoint, parallel to this second line that passing the two endpoint AB. So that tangent line is going to parallel to this second line over here. So f prime of C, it is the slope. That's the slope for the tangent line over here, f prime of C. And this one over here, this part over here, it is the slope for the secant line, for the secant line. Remember the slope formula, right? So FB minus FA, that is the rise from this point to this point. B minus A, that's a run from this point to this point. So rise over 1. It's kind of like y2 minus y1 over x2 minus x1. So FB minus FA over B minus A give you the slope for the secant line AB over here. So this says that this tangent line is going to be parallel to this secant line over here. If you relate this to Rolle theorem, so think about Rolle theorem right here. If you relate to Rolle theorem, think about you tilt it. So you take this to end, and then you tilt this at a certain angle. So before was horizontal, right? The base, and then you tilt the base like this, and now it's going to be not horizontal. Then what happens is this tangent line is going to be parallel to this secant line. So before was this. The secant line was horizontal, right? And then you have this tangent line is going to parallel to the secant line. So the slope for the tangent line is equal to 0. Now you tilt this base over here, okay? Then what happened here is this is still parallel to this, but now the slope of this tangent line is going to be equal to the slope for this secant line here. In other words, let's say there is at least a point, say P, so then the tangent line is going to parallel to this secant line over here. So sometimes you have only one point over here. The tangent line is parallel to the secant line. Sometimes you have more than one point, like 2 points. The tangent line here and here, both are parallel to this secant line that passing the 2 endpoints. That is the mean value theorem. So the mean value theorem says that F prime of C equal to this. What happens if you multiply both sides by B minus A? Multiply both sides by B minus A, you have FB minus FA, right, which is this, will be equal to F prime of C times this B minus A, right? This one and this one are equivalent. So sometimes you use this form, sometimes you use this form. This form is actually used more often. That was the mean value theorem. FB minus FA equal to F prime of C times B minus A. Now I want you to Google mean value theorem Beijing, right? You guys are on the computer, right? You guys can Google. So you Google mean value theorem Beijing and see what you find. Do you guys see this over here?
Yeah.
Yeah. You see this one. If you Google that, you find this. Okay, so what does it say? It says that the government of Beijing celebrate the mean value theorem, and the picture is taken a few blocks south of Tiananmen Square between Qianmen and the Temple of Heaven in Chongwen district of the city. And that was in 2008. And what do you see here? Do you see over here? On the bridge. What do you see? Can someone tell me? Can you read that over?
It's a formula.
It's a formula.
That's the formula.
Right? Okay, so what? FB minus
FA.
FA equal to F prime of sigma, but we just use C, it's the same thing, times parenthesis B minus A. So that is the mean value theorem that we talk about today. So it is so important. They actually put it on the bridge to celebrate that. Okay. I think it's very appropriate to put it on the bridge. Okay. It's appropriate to put on the bridge because think about this, right? Yeah, you look at this picture. Say the bridge is like this, right? The base might not be at the same level. This curve over here, it is continuous, right? It's not going to break in between, right? Okay, and it is differentiable, which means at any point the slope is going to exist. And when you walk along the bridge over here, somewhere between these two ends, the direction that you walk, this tangent line over here, is going to parallel to this base over here. So if you ever walk on a bridge, think about that. Maybe there's a moment, at that position, the tangent line is going to parallel to the base. So maybe that makes sense to put on a bridge. But imagine that you pass the bridge every day. and you go to work and go to school every day and you look at this mean value theorem, you probably remember that, right? Do you see that anywhere else in the world?
No,
No.
this is the first time I see it. Yeah.
They do that. It will be interesting. It was in 2008.
I think that's cool.
That's cool. Yeah, I just want to share this with you because I think it's interesting. So the proof of this mean value theorem, you can watch my later video. So I make a video for that. You guys just need to know how to use it. Okay, so I don't require you to prove it. So in this example, we're going to illustrate the mean value theorem with a specific function. So let's consider this cubic function, x cubed minus x, with a equal to 0, b equal to 2. So let's think about the mean value theorem. So first of all, is this function, does this function satisfy the two hypotheses of mean value theorem? So what are the two hypotheses of mean value theorem? Can everyone tell me? There are two. Number one.
Must be continuous and
Yeah. Number one, function has to be continuous on the closed interval, and at this time it will be 0 to 2. Number two, differentiable on the open interval.
yeah.
0 to 2, right? So number one, the function is continuous on 0 to 2 because this is a polynomial function, right? So yeah, so it has satisfied the first. Yeah. So because the function is a polynomial function, so it is continuous and also differentiable for all x. It is certainly continuous on this closed interval 0 to 2 and differentiable on 0 to 2. Okay, so satisfy the two hypotheses of the mean value theorem. So therefore, by the mean value theorem, there is a number c in AB. So therefore, by the mean value theorem, let's call the MVT. Okay, by the mean value theorem, there is a number c. Okay, I usually color coded that c in green color. Okay, c in this open interval such that b minus fa equal to f prime of c times b minus a, right? So in this case, b is 2, a is 0. So that is at least the number c in 0 to 2 such that f2 minus f0 equal to f prime of c times 2 minus 0. So that's the conclusion of the mean value theorem. Now f2, okay, how do you find f2? You substitute 2 into this x over here. So 2 cubed minus 2, that's equal to 6. F of 0, substitute here, you get 0. So f2 minus f of 0 here will be equal to 6. 6 minus 0 is 6. So the derivative of the function over here is x cubed, the derivative is 3x squared. The derivative of minus x is minus 1. So 3x squared minus 1. So f prime of c, then you will put the c over here. So over here, this will be 6. This over here, f of 0 will be 0. F prime of c will be 3 times c squared minus 1. That's f prime of c. And now times this 2. Then after that, that will simplify into this. So you multiply by the multiply 2 inside, you got this. Now you just need to solve this for c. To solve for c over here, you get 6c squared, that's equal to 8. So c squared is 8 over 6, which reduces to 4 over 3. Now, because this c over here had to 9 in 0 to 2, so we only take the positive root. So normally you get the true root, right? C is plus or minus square root of 4 over 3. Now because C has to be in this open interval 0 to 2, so the negative one doesn't lie in it. So C will be equal to positive square root of 4 over 3. So we only take the positive root. Over here, you look at the figure over here. So that's the graph for this cubic function. From 0 to 2, the function is continuous and differentiable. So that is this point C. And if you draw the tangent line over here, that is going to parallel to the second line that are passing the two endpoints. So here it is. See here it is positive square root of 4 over 3. This one here is square root of 4 over 6. That's a C. Question? Okay. All right. Great. Thank you. Now let's try to think about physics. Over here, if an object that is moving in a straight line with this position function ft, then the average velocity between A and B, and to find the average velocity, you just use the displacement divided by the time elapsed. The displacement, the change in the position, will be FB here, subtract FA. So that is this. And then divide by the time elapsed. So the time elapsed over here is B minus A. So divide by that, you get the average. So you get this average velocity over here. And the velocity at the moment C is f prime of C. Remember, first derivative of a position function is the velocity. So the velocity at the moment t equals C is f prime of C. So the mean value theorem says that if you travel in a straight line, sometimes between A and B, then the instantaneous velocity, maybe at this moment, say at this moment C, t equal to C. Now at this moment, the instantaneous velocity is going to equal to the average velocity for the whole trip. So that's what the mean value thing says. So my question for you guys over here, I want to ask you guys this. So I was traveling from San Francisco to LA. So the distance is 383.1 miles. I actually look it up by Google. And I say, well, I finished this trip over here in 5.5 hours. I go from here to here. Do you think I ever break the law by speeding over the speed limit along the way? What do you think? Will I get a speed ticket? What do you think? Tell me.
Probably not.
You're so kind. Probably not.
That's a good question. Yeah.
That's a good question. Did I ever go over the speed limit?
I don't know. Tell us, please.
You don't know. We can use a math skill to prove it. Okay. Oh, by the way, do you guys like this card that I drew? I drew this. You like it? Okay, that's good. All right. So what happened over here is actually we can prove that. Okay. Let's try to find out. Use the mean value here. So this is the distance. That's the time, right? Let's find out the average velocity for this whole trip. Okay. What was my average velocity? Well, to find average velocity, we use the distance divided by the time, right? So we had this, the distance here is 383.1 miles. Okay, and then divide by the time passed over here, it is what? 5.5 hours. Okay, get your calculator. Tell me what you get. That's about 70. Okay, so that's about 70 miles per hour. Okay, so the mean value theorem says that that is at least a moment, my speed at that instance is going to be equal to this average velocity. So at some moment, at least one moment, my speed it is 70 miles per hour. And look at the speed limit over here, right? My speed at that moment, my speed is over all this limit here. So I was speeding, okay? So the mean value theorem says that. So the mean value theorem says that there is at least a moment that my speed is about 70 miles per hour, which is over all this speed limit over here. So I was speeding, okay? So you can prove it. All right, so using math. Seems like using, so this crime scene, you can prove it, okay? Okay, you guys got it?